Hi, my name is Ming Yao, and this is part 3 of my Workbench simulation series.
The next step we want to do is investigate how this entire system responds to a drop simulation. So with our newly tuned resonator, which resonates in the right direction at the right frequency, let's perform a drop analysis. We start by compressing the spring using a static structural analysis. Here I'm setting up a brand new simulation because in a explicit dynamic analysis, we do need to ensure that our device is meshed using linear elements. But in addition to structural steel, we also want to include aluminum, copper alloy, let's do stainless steel, and for nonlinear materials, let's include nonlinear stainless steel for the springs. So that will be my setup for a static structural analysis. In the static structural analysis, I'm only going to compress a spring. I'm going to leave the rest of the device alone. So let's suppress everything else, and we'll set the spring thickness to the desired values. Springs will be made of nonlinear stainless steel. The oscillator, we have one part of it as a aluminum alloy, the other is steel. For meshing, we want to switch it to dropping the mid-side nose, thereby enforcing a linear element. Support on one end, put a displacement on the other end of the spring. 1, 0, 0. And again, we need to enforce the fixed rotation constraint on shell elements. So we have a deformation. It took a few steps because it's a nonlinear analysis with nonlinear materials, but you can see that it's still fairly linear. And it sets up the nonlinear criteria on basic models like this automatically. So from there, we need to include the rest of the housing. So let's go and find a mechanical model cell. So in this case, we ensure that the engineering data is the same, and our mechanical model here will only consist of the housing and the electric coil windings or electromagnets. I'm going to suppress these components, and the electromagnets on the inside will be made of copper, and we'll say the housing is made of stainless steel as well, but in this case linear stainless steel. Meshing, we want to drop the inside nose in order to enforce a linear mesh. Okay. So there was an error, but the simulation did get the part meshed. So from there we can do an explicit dynamics analysis where we take the deformed shape of the spring into our explicit dynamic analysis and we merge it with our housing to update the whole thing. So in this case, ANSYS will write out the deformed geometry loaded into my explicit dynamic analysis, and then it's going to add the housing mesh onto the same simulation. And let's take a look at where the explicit dynamic analysis ended up here. So we have the housing. You can see there are separate models here. On the mechanical side, it's a housing and 4 magnets. On the static structural side, there is the center mass as well as the leaf springs. We have a mechanical model contacts that shows us what are the contacts for the mechanical model. In this case, the contact between the magnets and the housing. Similarly, we have a set of contacts for automatically detected for the spring contacting the wall. There's two of them, one on each side. And then we have a set of contacts automatically detected for within our mass spring model. So everything looks like it's set up properly. All the materials have been brought in accurately. The mesh is created based on our previous mesh. Now we need to drop this against something. So it's typical in electronics drop testing to model a 1500G half sign shock spectrum. And we can put that through the mounting holes here. So we'll create yet a third piece and create a large mass based on that. So I'm going to duplicate this geometry and I'll edit it. SpaceClaim is the ANSYS Direct CAD modeler. And all I'm using it for here is to create a large mass on the bottom of this device. So I'm going to move this down a little bit, create some sort of a separation distance, and then let's find a rectangle from the center. So I'm going to make it by 100 by 100 and shoot it out by 100. So it's a nice solid block. I wanted a block that's much heavier and larger than the device itself, which means when I apply a force on this large block, I can calculate the acceleration that's applied to the entire structure. So I'm not going to use any of the other parts. Get rid of that. And that will now be the geometry that I use that represents the mass. So we do need another block for the mechanical model. And I'll create a very coarse mesh on this because this is a simple part that's not of significant interest to my analysis. This is just going to be a block to represent a large amount of weight. So again, dropped, and we'll put in a mesh sizing of say 50 millimeters. Now we can go into engineering data as well and modify, say, the density of this material. I'll make it 10 times denser, which means the mass will be much larger than my device that I'm than the device mass itself. Let's update this, which will cause it to import the new material model, then export that to my explicit dynamics analysis. And now I should have all the different parts. Now there's a big mass on the bottom. So the way we look at under the properties, the mass is 78 kilograms, whereas my housing, the other parts combined, is much smaller, on the order of thousands of kilograms. So my structure is much heavier than the other parts in my model, which allows me to use the large mass effect for the simulation. Have the mesh over here, and let's connect them together. So in order to connect the mass to my to the device here, I can use a remote point. Remote point allows me to tie all of these surfaces together in a rigid manner. Put this one on this. And I'm actually going to select all three surfaces. So there's one remote point that's going to be rigidly connected to all three, every node on all three of these surfaces at the behavior will be rigid so that it will not move, which means it's a rigid conductor that fully transmits whatever force is applied to this mass to the other structures. And we can make this mass rigid as well. There's an option here, I could have done it earlier, but in this case, it looks like it'll be a flexible body. But that's okay, the elements are so coarse that it won't affect the result significantly. I want to run this for a millisecond. I will select the bottom of this structure and assign a force. Typically for electronics drop simulations, we want a half sine 1500G acceleration curve that lasts half a millisecond. So I have half a millisecond here. In Excel, I've created a worksheet that calculates the curve for me based on the mass of this part. So force equals ma, which means the amount of force I am applying is the mass of my large block multiplied by the 1500G half sine acceleration. In ANSYS, we can copy this curve into this into a table here. So in the x-axis will be my time, and in the y-axis will be my acceleration in the z direction. So you can see we have a half a millisecond acceleration curve. We can choose to extend this to 2 or 3 milliseconds if needed. So once this is done, we can go ahead and run our simulation. I'm going to leave all the settings on default. Just go perform a run. So explicit analysis does take some time. It's dependent on the smallest element size in your model. In this case, it's going to take 11 minutes to run the simulation. It does provide a handy estimate of how much time is left. After a few minutes, the simulation is complete. Once the simulation is complete, we can take a look at the total deformation. Let's take a look at the deformation of the resonator system. We can adjust the number of frames as well as the length of the animation. This will allow us to determine how the part is moving during the shock event. This is all real deformation. So you can see the bowing due to the half a millisecond shock. We can take a look at the plastic strain that develops on the structure as it goes through the shock. This will allow us to understand whether there's any permanent deformations that will occur to the springs. And certainly any changes to the shape will affect the spring's future performance. And finally, we can take a look at the total acceleration. So the goal we're shooting for, and this acceleration is plotted on the support locations. You can see the goal we're shooting for is about 1500 G. It's not a clean half sine wave form, but it's fairly close, and we can make it more accurate by increasing the size of the mass and making it a rigid body. So this concludes my demonstration of the drop simulation. So in this analysis, we have taken a geometry and performed a pre-stress modal analysis followed by a harmonic simulation. We then performed a response surface-based optimization study to try to identify the right set of parameters that allow the resonator to resonate in the right direction at the right frequency. Once that's completed, we checked our results, then performed a explicit dynamics shock analysis to see how the resonator behaves during a shock event and whether any permanent deformation occurs.